The radar screen goes blank. For 8 critical seconds, every surface-to-air missile battery within 300 miles loses track of its target. When signals return, the weapon has vanished. Above the Pacific, something traveling at Mach 6 carves through atmosphere like a guided meteor. Inside, temperatures exceed 2,000 degrees Celsius. The guidance computer makes thousands of adjustments per second. Target acquisition in 90 seconds. No defense system on Earth was designed to stop this. 8:47 hours, Vandenberg Space Force Base, California, September 2025. This is the culmination of a secret arms race where America fell catastrophically behind. While the United States spent 2 decades fighting insurgencies in Middle Eastern deserts, Russia and China poured hundreds of billions into weapons that rewrite warfare's fundamental rules. Hypersonic missiles, systems traveling at 5 times the speed of sound or faster, threaten to render America's trillion-dollar missile defense architecture obsolete. The strategic equation is brutal: compressed decision times measured in minutes instead of hours, unpredictable trajectories that defeat tracking systems, weapons striking anywhere on Earth within 60 minutes. This isn't just another arms race. This is technological competition where second place means strategic irrelevance for the next half-century. Hypersonic weapons come in 2 fundamental forms. Hypersonic glide vehicles launch atop ballistic missiles separate at the edge of space, then glide through upper atmosphere at Mach 5 to Mach 20, maneuvering unpredictably toward targets. Hypersonic cruise missiles use scramjet engines, air-breathing propulsion systems that sustain Mach 5+ speeds at lower altitudes by compressing incoming air at supersonic velocities. Both types share one terrifying characteristic: they fly too fast and too low for traditional missile defenses to intercept. America's Aegis destroyers and Patriot batteries were engineered for predictable ballistic trajectories and subsonic cruise missiles. Hypersonics exploit the gap between those threats, surfing the atmosphere with plasma-cloaked agility that renders them nearly invisible to radar until seconds before impact. Compare this to what adversaries have already deployed. Russia's Avangard hypersonic glide vehicle entered combat duty in December 2019, riding atop ICBM boosters and reaching speeds approaching Mach 20 with the ability to maneuver during flight. Russia's 3M-22 Zircon cruise missile became operational in January 2023, launching from standard vertical tubes on frigates and submarines to strike targets at Mach 6 from 1,000 kilometers away. The Kinzhal air-launched missile has been used in combat over Ukraine. China's DF-17 medium-range ballistic missile, fielded around 2019, carries the DFZF hypersonic glide vehicle, a conventional weapon designed specifically to destroy American carrier strike groups before they can intervene in a Taiwan scenario. By 2021, China shocked Western intelligence by testing a fractional orbital bombardment system combined with a hypersonic glider, essentially launching a nuclear-capable weapon into orbit that could strike from any angle. Beijing conducted 20 times more hypersonic tests than America through the late 2010s, building an industrial ecosystem that dwarfs US capacity. And the United States, as of 2025, not one operational hypersonic weapon in the entire arsenal. 0. Pentagon programs reveal both towering ambition and grinding frustration. Lockheed Martin's AGM-183 ARRW, Air-Launched Rapid Response Weapon, was supposed to achieve initial operational capability by 2022. Test flights succeeded in demonstrating Mach 5+ speeds from B-52 bombers, but the program now faces potential cancellation amid cost overruns and unclear mission requirements. The Army and Navy are betting on the Common Hypersonic Glide Body, a rocket-boosted vehicle being integrated into the long-range hypersonic weapon and conventional prompt strike systems. The first Army battery began training in 2023, with full deployment planned for mid-decade. For air-breathing cruise missiles, the Air Force and DARPA achieved successful scramjet flight tests under the HAWC program in 2021 and 2022, leading to the Hypersonic Attack Cruise Missile contract awarded to Raytheon and Northrop Grumman. But even optimistic projections put operational capability in the late 2020s at earliest. The Pentagon's FY 2025 budget request for hypersonics hit $6.9 billion, nearly double the 2023 allocation, reflecting desperation to close a gap that widens each year. The development story exposes why America fell behind. Russian research on hypersonic technology traces to the 1980s, but Moscow accelerated dramatically after the United States withdrew from the ABM Treaty in 2002. Vladimir Putin explicitly linked hypersonic weapons to countering American missile defenses, warning that US systems could completely devalue Russia's nuclear potential without a countermeasure. China's motivations mirror Russia's. Hypersonics are seen as offsetting US military advantages in conventional forces and defeating missile defense networks. Both nations leveraged state-directed industrial bases. Russia's NPO Mashinostroyenia and Tactical Missiles Corporation, China's CASC and CASIC defense conglomerates, to transform theoretical research into deployed weapons within a decade. The United States struggled with fragmented programs across multiple military services, undefined mission requirements, and industrial bottlenecks that strangled production. Testing infrastructure became a critical constraint. Hypersonic development demands wind tunnels, simulating Mach 5 to Mach 20 conditions, but demand for tunnel time far exceeded supply, causing program delays. Manufacturing exotic materials at scale proved equally challenging. Hypersonic vehicles require niobium-based superalloys tolerating temperatures above 2,400 degrees Celsius, carbon-carbon composites for leading edges, and ultra-high temperature ceramics. The United States has no domestic niobium mining, relying on Brazil for 66% of imports, and Chinese companies have stakes in Brazilian mines. China controls 70% of rare earth element mining and 85% of global refining capacity, critical for thermal-resistant magnets in actuator systems. A single hypersonic missile requires components from thousands of suppliers across all 50 states. An Air Force solicitation in 2022 bluntly noted that expansion of industrial base capacity is required to achieve even 4 to 5 air-breathing hypersonic missiles per month, barely 50 weapons per year. Picture the operational scenario where these capabilities collide. South China Sea, 2033. A Chinese carrier strike group operates 200 nautical miles east of Taiwan. Type 052D destroyers bristling with HHQ-9 surface-to-air missiles, J-15 fighters maintaining combat air patrol, submarines lurking in thermal layers below. From their perspective, this represents an impenetrable defensive bubble. They don't see the 4 US hypersonic glide vehicles approaching from opposite vectors, each traveling at Mach 8, each guiding toward its target through real-time AI-driven course corrections. The lead weapon opens a crater in the carrier's flight deck before radar operators realize they're under attack. Secondary impacts disable escort destroyer radar arrays. Chinese fighters scramble, but the weapons that struck them have already disintegrated from atmospheric friction. The engagement lasted 4 minutes from first impact to last. No American aircraft penetrated the defensive perimeter, no pilots placed at risk, just precision mathematics and overwhelming speed. But the aftermath reveals true strategic danger. Chinese military commanders cannot distinguish between a conventional hypersonic strike and a nuclear one until after warheads detonate. The compressed decision timeline, minutes instead of 30-minute warnings traditional ICBMs provide, creates overwhelming pressures for hair-trigger responses. This dual capability blurs the line between strategic and tactical warfare, exponentially increasing the risk of miscalculation spiraling into nuclear exchange, neither side intended. The industrial ecosystem supporting America's hypersonic push reveals both extraordinary capability and dangerous vulnerability. At Lockheed Martin's facilities, teams assemble common hypersonic glide bodies using precision manufacturing techniques demanding tolerances measured in thousandths of inches. Raytheon and Northrop Grumman develop scramjet engines at facilities across Arizona and Massachusetts, but supply chains extend to specialized firms providing thermal batteries, ceramic tiles, carbon fiber composites, and guidance systems. The Pentagon's 2022 to 2027 Hypersonics Industrial Base Roadmap identifies critical weaknesses in sub-tier supplier development and proposes strategic investments to prevent single points of failure from strangling production. Behind these programs stand thousands of engineers and technicians. Materials scientists at Sandia National Lab design composites that survive re-entry heating. Software engineers at defense contractors Write algorithms that guide vehicles through plasma blackout conditions. Welders in Connecticut and Mississippi fabricate rocket motor casings. Test pilots at Edwards Air Force Base fly chase aircraft tracking hypersonic prototypes through their brief flight windows. These workers understand that every calculation, every weld, every line of code could determine whether America retains strategic overmatch in the 2030s. The hypersonic race forces fundamental questions about strategic stability. For 70 years, nuclear deterrence rested on mutual vulnerability. Hypersonic weapons with nuclear payloads undermine that equilibrium. If one nation possesses unstoppable first strike capability, does mutual assured destruction still deter? If defenses cannot reliably intercept hypersonics, does the offense-defense balance collapse entirely? Yet some analysts caution against hypersonic hype. Ukrainian forces successfully intercepted Russian Kinzhals using Patriot systems in 2023, proving even older defenses can adapt with proper tactics. Hypersonics face physical constraints. Extreme maneuvers bleed speed rapidly. Cost per unit likely reaches tens of millions of dollars, limiting procurement numbers. Advanced space-based sensors under development by the U.S. Space Development Agency promise to track hypersonic threats from orbit. New interceptors like the Glide Phase Interceptor could restore defensive balance by the early 2030s. The strategic verdict remains uncertain. What's undeniable is the transformation hypersonics impose on military planning worldwide. India develops the Mach 7 BrahMos 2 for 2028 deployment. Japan plans hypersonic gliders by 2026 and cruise missiles by 2030. France tested the VMAX glider in 2023. Even North Korea claims progress, though analysts assess they lag major powers by 5 to 10 years. The United States faces a choice-defining strategic competition for decades. Double down on offensive hypersonics to match adversaries, prioritize defensive systems and sensor networks, or pursue arms control before proliferation accelerates beyond control. Here's the question for you. If you advised the Pentagon on the next $10 billion allocation, would you invest in perfecting offensive hypersonic strike weapons to demonstrate credible deterrence, or in counter-hypersonic defenses protecting American forces and allies? Where does strategic advantage truly lie? In unstoppable offense or resilient defense? Let me know in the comments below. This is DIB Dispatch, where billion-dollar projects meet battlefield reality, and the future of warfare takes shape in workshops and test ranges most people never see.